Now we come to the second type of intermolecular interaction, dipole-dipole interaction. So it's the interaction between dipole molecules and dipole molecules. So two of the dipole molecules come close together with the Coulombic force. So we call this as dipole and dipole interaction. Very straightforward, isn't it? My example is this one, chloroform. The chloroform composed of one carbon atom, 3 chlorine atom, and 1 hydrogen atom. So what you can see here is the structure of the molecules is like tetrahedral structure. Okay? Every chemical bonding over here is polar bond, right? Because carbon has higher En than hydrogen atom. Then the electron cloud is pulled towards the carbon central carbon atom. And then carbon and chlorine atom. Chlorine has higher En comparing with carbon atom. Then 3 of the chlorine can then take away electron clouds from your carbon atom. So at the end, by vector summation of all the vector, the polarity vector of each chemical bonding over here. So in summation, the polarity of the molecules is go through the CH bond directly to the center between 3 of chlorine atoms and then go this direction, for example. So normally the symbol we are using is a kind of arrow with positive on the tails, right, indicating the negative charge and positive side. So we have dipole moment. The dipole meaning that we have 2 of the poles, positive pole on the hydrogen side and negative pole on the chlorine side. So this is the dipole molecules. So when we have 2 of the dipole molecules come closer together by the Coulombic force, positive and negative, we have interaction, we have attractive force, right? So they stay together. So this is called dipole-dipole interaction, which is very strong comparing with the London force, because the London force come with the electron dispersion, right, which is not permanent. Because, for example, the iodine molecules that I've already talked about it in the last video. So iodine molecules is like we have 2 iodine atoms with the same En. Then the electron distribution is quite homogeneous, but the electrostatic distribution is coming from the circulations of electron or the movement, randomly movements of the electrons inside. So we call it as dispersion force. So it's not permanent, but this one is quite permanent because the En is doing his job by pulling the electron clouds toward the chlorine atoms. So predominantly for chlorine side is negative and hydrogen side is positive. So this is relatively stronger than the London force. But anyway, because the dipole-dipole interactions, you have to know the dipole moment of the molecules by the vector summation. So first of all, you have to know the structure of the molecules by VSEPR. And then you can sum up the vector of the dipole moment of each particular chemical bonding, creating the dipole moment of the whole molecules, and you can compare. Now what I want you to do is to compare the boiling point of each pair, right, PF3 and PF5, SF4 and SF6. So first of all, you have to know the dipole moment of the molecules, right, by the vector summation and everything. So that's it. I will give you some time working on this, and then we'll come back here again in the next video to see the correct answer.